So I'm teaching the second class, which is on Riemann surfaces. So my understanding is this is supposed to be a more introductory level class, so I'm probably going to go at a slightly slower pace than Aaron did. And again, just to maybe make some comments, right? So Riemann surfaces are, it's a very classic subject. It concerns properties of surfaces with a sort of an additional structure that's natural, which we'll get to. And it sort of shows up in a lot of different areas of mathematics. And the main thing we're going to do is just give some, define them and prove some properties of them. And then the goal at the end of the class is to prove what's known as the uniformization theorem, which essentially classifies all of them. So it's nice. One of the nice things about Riemann surfaces is, at least for certain things, you have a very nice, complete answer, which we'll hopefully get to. And then maybe I wrote some exercises which will relate the Riemann surfaces to some other problems in geometry. Okay, so let's get started. So maybe just to give, as I said, a little bit of motivation. So Riemann surfaces kind of show up in two. I mean, they show up in a lot of different areas, but the two areas I think we'll probably focus on is, on the one hand, they show up in what you might consider sort of complex analysis. Right, so this is the theory of, say, one complex variable. In particular, we're going to have maybe two places where we're going to look at them. So the first is maybe if we want to, say, solve, polynomials equations into, let's say, complex variables. Right, so we want to look at, say, the zero set, say, ZW in C2 of some polynomial. The idea is that somehow the zero set is supposed to be a complex codimension, one object in which, since this is two dimensions, should be one complex dimensions, which is essentially a surface. So that's a Riemann surface. And I mean, of course, you can just formulate this as a much, more classical question. So maybe like a prototypical example would be to just consider the following very simple equation, which is P of ZW is W squared plus Z. Right. So if you want to try and find the zero set of that, I mean, one thing you might try and do is find it. Solve for W as a sort of function of Z, right, which we know how to do, and that's heuristically we would expect W to be. But this is, of course, a little bit ambiguous, as you probably recall from complex analysis, right? So if you're away from the origin, so in the punctured complex plane, and you choose a point there, you can locally make sense of the square root, right, around any point, but you probably recall that there's no global way to make sense of the square root, right? If you try and say if you tried to have, the issue is that there's an ambiguity in which sign you take, and if you tried to patch together all these local choices, when you came back around a path that went around the origin, you'd end up with the opposite of what you started with. So the point is there's no global way of making sense of this on the punctured complex plane, but it would be nice to have a kind of global perspective on this, and this is one of the things we'll see Riemann surfaces allow us to do. So that's one example. So another very similar example is to sort of look at solutions to complex ordinary differential equations where some of the similar issues arise. So again, a very simple example, which I don't want to, is to consider, say, the equation dw dz is equal to 1 over z, right? So again, locally, on this punctured complex plane, right, we can think of a solution W, right? I mean, that's essentially the definition of the logarithm. But again, this only makes sense if you choose a point in a neighborhood of the point, and you kind of can't globally patch it together because, again, if you go around the origin, you'll end up not where you started, but at a different function. I mean, a different value, a value that differs by 2 pi, up or down. So again, if you want to try and understand a kind of global theory for these sorts of ordinary differential equations, you're going to have to introduce something more general than just looking at the complex plane. And again, that's where Riemann surfaces come in. So this is sort of maybe one perspective, which is probably a perspective I'm not as interested in, so I won't emphasize it as much. The other perspective is from differential geometry. So there's two things here which will be relevant. So the one is, as I said, a Riemann surface is a surface with an additional structure. And that additional structure is a sort of notion of complex structure in some sense, which I'll make that precise. So it turns out that if you're interested in what's known as complex geometry, which I guess one of the classes will be on, so the point is a Riemann surface is a one-dimensional complex manifold. In other words, it's sort of the simplest possible setting to look at complex geometry. And the point is, in one-dimensional real geometry, is curves. There's basically nothing to say. But it's already, in this one-dimensional complex geometry, this is already a pretty rich theory. So the other perspective is what's known as a conformal geometry. So here, the idea is you have a surface where you can measure angles, but not distance. Right. So, to measure distance, say on a surface or manifold, you need to have a Riemannian metric, for example. But it turns out that you don't need you need much less information if you just want to measure angles. Right. So the idea is, if you have a Riemannian metric and you multiply that metric by a smooth function, that gives you a new Riemannian metric. And of course, the notion of distance is completely changed because you're scaling the length scales. But if you work out, just like the formula for how angles relate, like from, say, the cosine law, it turns out that multiplying doesn't change anything. So when you take this sort of equivalence class of metrics where you say two metrics are equivalent if they're a multiple, one is a multiple of the other by a smooth positive function, then that gives you what's known as a conformal structure. And as we'll see, in 2 dimensions, modulo a slight technical issue I'll come to, the conformal structures on a surface are equivalent to the Riemann surface structure. So what happens is in this low dimension, you have this you can think of complex geometry and conformal geometry as the same. And this is allows a lot of remarkable things to be done in 2 dimensions that are not true in higher dimensions, because this equivalence gets broken in higher dimensions. And in fact, there's no real reason to expect there to be much in common in higher dimensions. Okay, but because of these facts, when you want to sort of prove things about surfaces, you often, even sort of purely geometric things about surfaces, it's often very useful to go to this Riemann surface picture, as we'll maybe see in the last lecture. Okay, so that's just maybe some propaganda that has no meaning. So the first thing I want to talk about today is just to give some definitions and try and make sure we're all on the same page, since I don't know everyone's background. Okay, right. So to begin, We're just going to start with some definitions of a set of objects to study. Okay, so the first thing I want to define is what I mean precisely by a surface. So if you've probably most of you know what a manifold is. So for me, a surface is just a two-dimensional manifold, but since I don't know if everyone's seen that, and it's useful to refresh our memory since it'll help us in understanding the Riemann surface definition, I'll go over that. Of course, we have this intuitive idea of what a surface is when we're inside of R3, right? I mean, like the sphere. I'll just draw a picture, right? Right, that should be a surface. And the idea is we want to kind of abstract away all the irrelevant information and focus just on what, for us, is the important thing about being a surface. And that's, for us, it turns out to be the notion of how to talk about smoothness. Right, so that's what we're going to do. So we start with our definition. So, and okay, so we're going to have three pieces of information, essentially. One, so the first is going to be X, which is going to be a Hausdorff second countable topological space. Okay, so just a topological space with some technical conditions, which we won't focus too much on. The second thing is going to be a choice of open cover. So choice where alpha is some index set of X. And then these are not very interesting. The kicker will be this third condition, which is what's known as an atlas. So we're going to have homeomorphisms phi alpha that take the U alpha to sets U alpha tilde that are open in R2. And the condition that is very going to be important, and we'll come back to this, is that if we look at these so-called transition maps, which is phi beta composed with phi alpha inverse, which take certain so this is supposed to be our smooth maps. Right, and these are just subsets of R2, right, if you look at the definition. Right, and I just want to say, I mean, these could be empty sets, in which case this is vacuous. But if they're not empty, then they should be, this has content. And the point is, right, we can think about, once we know what these, this condition will allow us to actually define what it means to be smooth on this surface X, whereas with just the topology, we would just know what a continuous function is. So let me just give some terminology, right? So this object, which is U alpha tilde phi alpha, this is a chart, and the collection of all of the charts is sometimes a smooth atlas. Okay? And I just want to, this is a technical point, but again, it's worth remarking on, right? Of course, in part of our data of a surface is, of course, this choice of atlas. And you could wonder if you choose different, it's sort of not very profound observation, but if you choose a different atlas, you technically get a different structure. But of course, we don't want to kind of make such a fine distinction. And so we're usually going to identify two surfaces if there's a map between them which is smooth. And of course, what does it mean for a map, and has smooth inverse? And what does it mean, of course, for a map between these surfaces to be smooth? It just means that it's smooth in the charts, which by this, one can check by star, and the chain rule, checking that something's smooth is well defined. So I won't, you probably have all seen this, but I just want to remark this. Of course, there's something a little profound in this in higher dimensions where you could actually have inequivalent structures in the same topological space, but it turns out that that doesn't happen in 2 dimensions. So I don't want to go into that. Okay, so what are some examples, just to, always good to have examples. Some examples. All right, so of course any open subset of R2, right? So we just take the chart, which is the open subset, and use the map phi to just be the identity map. So for example, right, we could take what might be called the unit disk, which is, right, which of course is the same as all of R2, one should check. Or, for example, the annulus. This is the annulus. A slightly more interesting example is the Mobius band. We'll come back to this. Right, so this is where you take a region in the plane, and you sort of you cut out this rectangle, and then you glue it together, but you put a twist in. Right, you've probably all seen this. And then, of course, I mean, going back to this sort of intuitive notion, if you just take a function f from R3 to R, which is C infinity, then if 0 is a regular value, which is, so that the derivative of f is surjective, then the preimage of 0 will be a surface. Okay. So for example, I mean, that gives us lots of examples. Okay, so that's just what we mean by surface. Now, what we're going to see is that we're going to focus on this condition star and ask, well, what happens if we know we have all this notion for smooth, but smooth functions are fairly flabby, right? So we could ask, what happens if we sort of restrict the functions to be in a more rigid class? So it turns out that if you restrict the functions to be in a more rigid class, then in fact, what's going to happen is, as long as that class has a good behavior under composition of functions, so in the case of smooth, that's the chain rule, then what that should do is it's going to actually induce a structure on the space X, which is sort of more refined than the smooth structure. So eventually we're going to see that this Riemann surface structure is such an example where we restrict to the phis so that the transition maps are in fact holomorphic, which of course is much stronger than being smooth. But maybe to just give you a feel for certain things, I want to give some other examples, which again probably a lot of you have seen, but it's just worth it to remind everyone. Okay, so let's give some examples of strengthenings. Okay, so the first example is to do the following, which is right here we're just saying they're smooth, but there's a lot of big class of smooth functions. So the first thing we're going to do is say we say a surface M. Well, we say, let me say, how do I want to say this? So an oriented surface is a surface with an oriented atlas. So in this case, i.e., we replace, so we take the same definition, but we replace star by smooth, so it's still smooth, but we impose an additional condition plus that the Jacobian of the transition maps is positive. Okay? Okay, so what this means is that what you should remember is, I mean, there's certainly smooth maps where this is not true. And so this is imposing a restriction because we're choosing an atlas with more properties than just the transition maps are smooth. And one of the things you should remember is that by choosing a positive Jacobian, that means that the sense of sort of clockwise and counterclockwise is preserved under application of the map. And so what this means, kind of going back to the surface, is that on the surface we have a well-defined notion around each point of what it means to go clockwise or counterclockwise. But of course, and the thing that turns out to be true, and you should always remember this, is when we're making a bigger restriction on the atlas, that means on the one hand, there's two things. On the one hand, it's harder to have such an atlas. So there may be sort of things that have a smooth atlas but don't have an oriented atlas. And of course, you all know this, so the example would be the Mobius band does not have an oriented atlas. You should convince yourself of that. On the other hand, and this is a little more subtle in this oriented case, but it's much easier to have inequivalent atlases, right? So I'll sketch a proof of this later. It turns out that if you have one smooth atlas, then essentially all the smooth atlases are equivalent. But you can see that, of course, if you have an oriented atlas on, say, a connected manifold, a connected surface, in fact, there's sort of two inequivalent choices of atlas, which is one where you choose every point to be, say, clockwise, and then where you reverse the orientation and everything's counterclockwise. And again, when I say equivalent, I mean, right, just as you can check smooth by looking in local coordinates, when you have two oriented manifolds, you can check smooth plus orientation preserving by checking in the oriented atlases. So you should see how to do that again. Okay, so again, these, making the restriction of smooth is pretty flabby, and putting this condition of positive Jacobian is still pretty flabby. So one can actually go to a really extreme case, which is to restrict these transition maps to, in fact, be, say, isometries, right? So that's a very small. There's an infinite number of smooth maps, but there's really a finite, an infinite dimensional space of smooth maps, but there's really just a finite dimensional space of isometries. So we say a flat surface is a surface with a flat atlas, i.e., the transition functions are isometries. Right? So notice, in principle, a flat surface doesn't need to be an oriented surface. So you can also talk about an oriented flat surface by imposing even further that they're orientation-preserving isometries. But I don't want to go into that. So of course, if you're forcing the transition maps to be isometries, one of the things that means is that basically if you have a metric, if you pull back, say, just a Euclidean metric to the surface by one coordinate chart, then if you pull back it by another coordinate chart, then the two choices are consistent. So what this means is you could actually patch together a metric on the surface so that when it arises from being pulled back from the Euclidean metric by all the coordinate charts. So what this means sort of geometrically is this will be an exercise, but so a flat surface is the same essentially as a surface with a Riemannian metric with vanishing curvature. Okay, so, and I mean, you probably, if you've seen any Riemannian geometry, you know that this is a very strong condition. So, for example, just by the Gauss-Bonnet formula, there's no way that there's such a metric on the two-sphere. So this is an example where you have this very rigid structure, and it really restricts the possible surfaces which admit such an atlas. On the other hand, you could it's pretty clear to see that the torus admits such a surface just by taking the quotient by a lattice. So you get a metric induced by Euclidean space. And it's not too hard to see that essentially, there's very few lattices which will, when you take a quotient, give you the same torus, right? For example, something like the volume would have to be the same, and the length of the sort of two lengths of the lattice would have to be the same. So it turns out in this case, there's the moduli space. In other words, the space of flat surfaces up to equivalence is on a torus is fairly big. So again, we see this sort of dichotomy. Okay, so that's this is maybe too extreme since it's too restrictive. So the third example, which is going to get us closer to what we want. So a conformal surface is a surface with an atlas, a conformal atlas. I.e., one where sort of infinitesimal angles Okay, so again, the idea is when you look at the transition functions, essentially the transition functions, if you have an angle, the angle is sort of preserved under in the transition functions. And again, what this means is if you patch everything together, it means that on a conformal surface, there's a notion of angle, even though there's not a notion of distance. So you don't get a Riemannian metric, but you do get this, as I alluded to, this conformal structure. So again, the exercise, and there's two parts. So one part is easy. So a conformal structure goes to a conformal atlas goes to a conformal class structure, say. Right, so for me, this is just an equivalence class of metrics, Riemannian metrics, where you have G1 is equivalent to G2 if and only if G1 is equal to e to the lambda G2 for lambda C infinite function. Right, so right, just as you could use the charts to pull back this metric when you're in the flat case, you can use the charts to pull back a conformal structure in the conformal case. Now, and this is really the importance of being in dimension 2. In fact, you can go the other way, modulo, right? So, but this is really only in dimension 2. So the exercises we will have that, and it turns out this actually uses some PDE theory to see, right? So it turns out that in this case, a conformal surface is the same as having a conformal class, and this is really one of the powers of Riemann surfaces is this fact, and why they're so important in dimension 2. So why of course is this is this relevant to Riemann surfaces? So that's the fourth example. Okay, so remember, R2 can sort of be uniquely identified with C by just saying xy goes to x plus iy, right? And there's no information here. But the point is we can always think of an R2 map. So a map from between open domains of R2 is a C map, which is to say a map between open domains in C. And the point is if you should sort of recall, well, right, when you talk about C maps, right, of course you have the notion of holomorphic, which is to say a map is holomorphic if it's a complex differentiable. And of course we could ask, because we have a chain rule for holomorphic maps, we can of course put the restriction that that star in this case actually be holomorphic maps. So this is the final example, which is a Riemann surface is a surface with a holomorphic right. So in other words, we have coordinates, these phi alphas, and when we look at the transition maps, these are holomorphic maps. And as I alluded to, right, you probably you should recall or maybe verify this. Maybe in the TAs will do this, right? One way to characterize holomorphic maps, just in C, so a holomorphic map is an orientation preserving conformal map. Right? You should check this, but it's probably something you recall if you took any complex variables class. So one of the ways of thinking of a holomorphic map is if you think of it as an R2 map, it again preserves angles infinitesimally. So the point is, for what this means is, and this is something we'll for the most part, we won't think about this in the lectures. We'll just focus on this. This is sort of the complex geometry point of view, where you have a holomorphic atlas. But when you actually, in the end, when we want to try and get some geometric applications, we're going to use the fact that these 4 and 3 is the same as 3 plus orientation. So that, in fact, we can say things about the conformal structure of a surface by appealing to facts about the Riemann surface structure. So there's I have some exercises where you can try and work this out a bit. Okay, so that being said, right, we're now really focusing on this guy, right, these Riemann surfaces. And again, just as in the smooth case, where we can check whether a map between smooth surfaces is itself smooth by looking in charts, we can check whether a map between Riemann surfaces is holomorphic by checking in these holomorphic charts corresponding to the holomorphic atlas. And right, again, by the chain rule, that's a well-defined notion. So again, we're going to kind of always make this tacit assumption. We identify Riemann surfaces if they're bi-holomorphic. In other words, if there's a holomorphic map between them with holomorphic inverse. So the questions then is we've introduced this object, which is a refinement of the notion of surface. So we're led to sort of, again, this question of when do we have such a structure and how many such structures do we have? So again, the questions we're really going to sort of look at. So the one is, what and a sort of, so this is a question about sort of the essentially what smooth surfaces can be thought of as Riemann surfaces, and then a more general question, which of course is harder, is can we classify? Okay. So the first this first guy has a very, as we've already just seen by this observation over here, right? A holomorphic map is automatically preserves orientation. So that automatically means that a holomorphic atlas is an orientable atlas, right? So that means that one has an obvious necessary condition. Right? That, in other words, that the surface is orientable. So it turns out that this actually is a sufficient condition, but that it should not be immediately obvious to you. So we'll eventually, again, one way to see this, which of course has, I'm leaving a lot out, but one way to see that this is a sufficient condition is the following. So, right, remember by something, this identification between Riemann surfaces and conformal surfaces, it should be enough to prove that if you have an orientable surface, if you can make it a conformal surface, then you can make it you can make it a Riemann surface. So the question is, why can you make it a conformal surface? Well, again, and this is the hard part, is this direction, which I haven't alluded to. If you remember from Riemannian geometry, it's for any manifold, one can put a Riemann metric on it, right, by just patching together in charts. So that means if we have a metric, then we can get a conformal structure just by taking the equivalence class of the metric, and then that should give us a conformal atlas. But again, here we're using that we're in 2D. And then we know that these conformal surfaces that are orientable, which we're assuming, they should actually give us a holomorphic atlas. So this is actually quite a bit more subtle to prove that this is sufficient. And in the end, it's a little bit easier, and we'll probably just look at the case where the surfaces are closed. So there, it'll be simpler to see that this is true. But you should remember this is a reasonable question to ask. The second part is what the most of the course is going to be, and this is what's known as, as I said, this uniformization theorem. Yep.
About G1 and G2, are they the pullbacks of the Riemannian, the Euclidean metric to local pullbacks, so that they will be related by multiplying by lambda?
Sorry?
G1 and G2, what are they?
So I'm just saying a conformal structure is essentially an equivalence class of Riemannian metrics. So I don't say anything about what.
It's not the pullback. It is not obtained by pulling back locally the Euclidean metric. It's not.
So that's essentially what this is saying, that you can do that in 2D. But in general, like this makes sense in any dimension, and it turns out in higher dimensions you wouldn't expect that these metrics would a conformal class wouldn't necessarily get pulled back from a Euclidean one. Okay, so this is the uniformization. Right, so what we want to do here is we want to classify as we see, by this part one, the only condition we need to put on the surface is that it be orientable. And then the uniformization theorem basically is going to tell us more or less how many different inequivalent Riemann surface structures can possibly exist on a given orientable surface, right? Right. So, but of course, I mean, the first step in all of this, of course, which is what I'm going to spend the last 15 minutes on, is right, the uniformization theorem. I mean, there's going to be what turns out for us to be an easy case, which is classify the surfaces, and then the hard part will be to sort of classify on the surface how many different inequivalent holomorphic atlases there are. Okay, so that's the final part of today. So we're going to take this guy. Okay, so the classification. Okay. Okay, so in order to sort of describe this, let's just be a little pedantic and remind ourselves of what our building blocks are, right? So our building blocks, to try and do this classification, we have the following three building blocks. Okay, so the first one is S2, which is say the unit sphere in R3, which is, of course, you should check is a smooth surface, the unit sphere, the sphere. The next building block is what's known as the 2 torus. Right, this is the torus. Right, so you can think of this as either the product of two circles or as the quotient of R2 by a lattice. Right, so in other words, a kind of where you identify these two ends. And then the final building block is going to be RP2, which is the real projective space. Right, so this is, you can think of this as either the space of lines in R3 or equivalently as the sphere S2 where you identify antipodal points. And the distinction between RP2 and S2 and T2 is that RP2, these are both can be thought of as oriented surfaces, whereas this cannot be. So that's the distinction. So one thing that, of course, makes this tricky to visualize versus these other two, where we have, clear pictures of them. And this is certainly a fact, but a fact is that the RP2 cannot be embedded in R3. So it's hard. You can only visualize it by allowing surfaces with self-intersection. So that gets a little tricky. Okay, but once we have these building blocks, what we're going to do is we want to be able to build more complicated surfaces out of them. So again, this is going to be a little vague. Okay, so given two surfaces, sigma 1 and sigma 2, right, we define a new surface which is called the connect sum of the two. This is the connect sum. So I'm just going to do this pictorially and leave it to you to make this rigorous. So you start with these two surfaces, sigma 1 and sigma 2, and you find disks in them. just pick them. So these are disks. And what you do is you're just going to delete the disks. And then you're going to glue in an annulus. So you've deleted the two disks and replaced them with an annulus. So now you go from two disconnected surfaces to one connected surface. So this is the connect sum. And of course, it's an exercise. Well, first of all, to formulate this, rigorously and check that it's well defined. Right. I mean, we're in principle making a lot of choices, so we need to check that the choices don't affect anything. And then it turns out this operation is almost like it has a lot of properties that you might expect from, say, an addition, except for you can't invert. But so, for example, this operation is commutative. That should be easy to see, and associative. And this sort of identity element, which you should convince yourself of, is the sphere. So if you take the connect sum of sigma 1 with a S2, then you just get sigma 1 back. OK, so that's this notion of connect sum. And we're going to use this now to kind of inductively build up what turns out to be all closed surfaces. OK, so we're going to define two classes of surfaces. OK, so we have the sigma g, which is defined so that sigma 0 is equal to S2, and then sigma g is inductively defined to be sigma g minus 1, connect sum this 2 torus. OK, so the picture here is you're supposed to have right. So here's like sigma 3, right? So you've taken a torus. I mean, and then here's like your sphere to start it off, right? Right. So each of these are next, where you've added 3 toruses, and the point is G is called the genus. And equivalently, we're going to have this chi h, which is defined so that chi h is defined so that chi 1 is RP2, and then chi h is chi h minus 1 connect sum RP2. OK. So again, I won't draw this. And the h here is either also called the genus again, or sometimes called the demi-genus. OK, so then the theorem, which right, I mean, is again one of these remarkable things about surfaces is we have this complete topological classification that's relatively simple, involving only more or less an integer invariant and a parity. So we have this theorem, which is the classification. OK, so let sigma be a closed. So closed means compact and without boundary. Or another, really, the without boundary is redundant, but just say it's a compact surface, a closed connected surface. Then if sigma is orientable, so in other words, if it admits an what did I call it, an orientable atlas, then sigma equals sigma g for some g. Sigma is non-orientable, so it does not admit such an atlas. Then, sorry. OK. we have a complete description of closed surfaces, which is, as I said, they're essentially an integer invariant determines them along with the parity, whether they're orientable or not. So just an aside, right? You might wonder if there's a comparable result for all surfaces. Well, it's a little tricky because, of course, you can remove any closed subset from a manifold or a surface, and that will still be a surface. So, for example, you can just remove very complicated sets like a Cantor set and get a surface that's not closed. Or equivalently, I mean, you can imagine situations where you take a sort of infinite sequence of connect sums. You can construct surfaces with sort of infinite genus, and a bit tricky to sort of specify all of those. So that's why we restrict attention to the closed case. Okay, so I have, I guess, 5 minutes, so maybe I'll just try and very briefly describe the ingredients of the proof. And of course, maybe I'll just focus on the orientable case because, of course, this non-orientable case is never going to occur when we look at Riemann surfaces. Okay, so a proof. What we're going to do is we're going to pick. What we want to do is try and decompose the surface sigma into simple pieces, which then we can just sort of essentially combinatorially see how they fit back together, and see that essentially the only ways they can fit together is if it's one of these standard guys we've constructed. And the way we're going to do that is we're going to use what's called a Morse function. Right, so the proof is we're going to pick, and this is obviously a slightly loaded statement, but a Morse function on sigma. So that's in other words, i.e. C infinite function such that the critical points, right? So here F. So here F is supposed to be a map of sigma into R. So one thing we should notice is that if you have a smooth function on a surface, you can check whether its derivative is 0 by just looking at charts, and that's independent of the choice of chart. That's the only value of the derivative that makes sense. But that means the notion of critical point is well defined. So the set of critical points is finite, and we also assume that if the map F taking the critical points to the critical values, we'll call, say, C tilde, is an injection. So for each critical value, there's only one critical point. And then the final condition is that we want to assume that if P is a critical point, then there is a chart about P such that in this chart, we have that so in this chart we have that F is equal to f of p plus either x squared plus y squared. So x and y are going to be the sort of standard Euclidean coordinates on the chart. So this is the first case. One of the following three happens, f of p and the idea is we're supposed to say that x of p, right? So we're picking a good chart to sort of simplify f. And of course, that such a chart exists is not completely obvious. I mean, that such a function exists is not obvious, but is true. So the idea is when you look at this, this function, by looking at sort of how the sort of level sets of this function change on sigma, it allows you to break the surface into essentially 5 standard pieces. So what do I mean by that? So let's say pick an interval I inside of R such that the I intersect the critical values is either empty or 1 point, right? So then what we can see is that for such an I, one should check is that f inverse of I is going to be equal to the following sort of 5 things. So the first is it's a disk like so, in the sense that there's nothing above. Well, plus, if you look at each component, so there's going to be a lot of annuli over here, potentially. So if the component doesn't meet a critical point, then it's an annulus. You should convince yourself that. Otherwise, it's a disk like this. The second case is this corresponds to something like this guy. Right. Yeah. It could also be a disk like this, plus, again, some annulus components. Could just be an annulus, right? So again, with some annulus components. This would be the case if there's no I is disjoint from the critical values. Then the fourth is, again, there's sort of 2 cases here which correspond to this sort of saddle point, which is you could get a pair of pants like so, or flip it around, but a pair of pants. And again, plus other stuff that's an annulus. And then the other cases, which I won't draw, is you can get a Mobius band, or the 6th component is a Mobius band minus a disk. Okay, so there's actually essentially six standard pieces. And the point, though, is one should prove this, is that a Mobius band can only arise inside of a surface if the surface is not orientable. So in the oriented case, this never occurs. And so then you just have these standard pieces which you have to figure out how they get pieced together. So that's a little bit involved, and I don't have time. But let me just give an illustration just so you can get the idea, right? So let's start with a torus, right? And let's use our Morse function as just a height function. So f is equal to the height. Right, so the critical point here, 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 here. And as we look at the standard pieces at the top, we get this disk, right? Then here we get an annulus. Right, so between here and then at this level, we get a pair of pants. Right, here's our critical point. Then that pair of pants is glued to another pair of pants, which again corresponds to a critical point. And then at the end, I mean, we could have another annulus, or we could just think of it as capping off the disk. So of course, I mean, in general, things could be much more complicated, and it's much less clear how. I mean, one has to sort of also figure out how this decomposition relates to this connect sum decomposition. But for example, Donaldson gives a kind of outline of how to do that. And maybe it's a useful exercise to try and convince yourself of this without, basically just draw some pictures and try and see how things fit together. Of course, I'm not really a topologist because I find these arguments highly non-rigorous. So, all right, that's that. So I'll stop here. Yep.
The top annulus, is that also optional?
Yeah, that's optional. I just wanted to sort of illustrate that. Basically, what happens is if there's no critical points, there's nothing really happening. So you would get an annulus, say, but somehow there's no. You could just, if you glue an annulus onto a disk, you just get a bigger disk. Or you glue an annulus onto a pair of pants, you just get a bigger pair of pants. So there's sort of, the annulus in this setup is sort of like the sphere, has no content. Sorry? So the first three is you have, so remember, at any critical value, you could have a lot of disjoint components. So the point is, by our assumption, though, there's only one critical point for each critical value. So maybe this is confusing. So at a critical value, right, you should get sort of some change of topology, but the other possible components will just be annuli, and so not have any information. So these are sort of optional. And then so just focus on the interesting parts. Let's ignore this because it's sort of silly because there's nothing happening here. So you can either have a kind of nothing become a disk, which corresponds to, right? If you're too big here, there's no way to solve. This only has a solution on a fixed disk when x and y are sufficiently small, right? So if you're too big, there's no solution, so you're empty. And then as you get smaller and smaller, eventually you hit a point where it exists, and then from then on, the level set should be a circle, which is what you have here with the disk. Then similarly, in this third case, the opposite sort of happens. So you get a disk kind of going down. Third case is there's no critical point, so there's nothing interesting. And then in the fourth case, you have a kind of a saddle type point. And it's actually, what basically is happening, what's basically happening is you have this sort of saddle point. So you have, you can think of it as sort of the upper level set. These are sort of and then the lower level set. And this is the zero level. This is sort of the zero level set, if you like. And so the pair of pants is sort of, you're kind of doing this and doing this, where you have this very clear description of things here, and then you kind of glue in a ribbon. So this is like the pair of pants. But these Mobius bands, what happens is when you could also, it's harder to visualize, but of course there's no reason that this strip here has to be glued in the way I drew it. You could also glue it in with a twist. And that's where if you kept this one the same and glued this one in with a twist, that would be the Mobius band minus a disk. But if you glued this one in with a twist and this one in with a twist, that's where you would just get the Mobius band, if you work out how it goes. Does that make sense? But of course, as I said, these are sort of the non-orientable case. So for our purposes, we can kind of ignore them. But
I'm not sure I understand case 5. The Mobius band only has one boundary component.
yeah.
Whereas the interval has 2, and you would expect somehow that there's...
Well, you just think of this guy. This has one boundary component. So.
Yeah, so...
Right, the problem is, right, probably your intuition is coming from, say, submanifolds of R3. But of course, one way to think about it is you can get RP2 by taking the Mobius band and gluing a disk onto the boundary of the Mobius.
Is there a critical value, a critical point of the function somewhere in the interior of the Mobius band, though? Is that what's happening? Yeah,
exactly. So take this picture, which is kind of like here's the critical point, and then you have, it's hard to, here's this and here's this, and then not like I have any idea of what this means, but what happens with the Mobius band is you sort of take this and go like this, and then take this. It's hard to...
Okay, I guess the point is that a Mobius band is compact
Well, I mean, it's not achieved. I mean, this is a saddle point, so it's not.
This isn't a picture of a movie span, though. That's something else.
Well, so if you take the strip and you twist it, right?
So it's intersecting itself also? Or?
Well, it's not. I mean, the problem is I'm trying to draw something on a board that's representing something in R3 that doesn't really exist in R3. So it's a little. I mean, it's going. I mean, the function is not like a height. It's. I actually was confused about this for a while, so I understand. But if you take it and you kind of go and go like this, and then you kind of take this piece and go like this, you can see that everything kind of works out, but maybe this is not the best way to explain this. I mean, I see what you're worried about. Yeah, let me maybe get back to you about that. I'm having a bit of a. I see what you're worried about, though. Yep. So when you look at a regular value of. Mm-hmm. Well, yeah. So I mean, that's definitely not trivial to do. I mean, mathematically, that's where you have to do a little bit of work. But so this is called like the Morse lemma, I think. No, maybe that's not what it's called. Sorry, I'm bad with names. Yeah, Morse lemma. Okay. It's like a kind of it's like a standard form for a function with a non-degenerate critical point. So, well, I mean, we'll see something very similar to this in the context of complex analysis. So, you should sort of. I mean, the proof is the idea. I mean, the proof is going to be different, but the ideas are very similar. Okay, that's everyone happy.